Hello everyone. In this section, we will use Cramer's rule to solve linear system Ax equals b. And we will also introduce a new formula for A inverse. It helps you to find the A inverse by compute the cofactor matrix and determinant of A. Okay, so first let's see the definition of Cramer's rule. If determinant A is non-zero, which also means A is invertible or non-singular, the linear system Ax equals b is solved by determinant x1 equals determinant b1 over determinant A, or generally xi equals determinant bi over determinant A. Okay, here the xi is the ith entry of solution vector x. And the matrix Bi has a S column of A replaced by the vector B. Okay, and there's a really important thing is if you want to use Cramer's rule to solve the linear system, your matrix A has to satisfy this condition. So the determinant A is not zero. Okay. Okay. Let's see. Here's examples here. So this is matrix A, and this is vector X, and this is vector B. Okay, and for finding the solutions x1, x2, x3, we first need to find the b1, b2, b3. Okay, so b1 is obtained by replacing the first column of A by B by vector B. So which means replace A1, 1, A2, 1, A3, 1 by B1, B2, B3. Okay, so this is B1. B2 is obtained by replace a second column of A by B1, B2, B3 by B. Okay, and B3 is obtained by replacing the third column of A by B. Okay, and then we use the formulas, the Cramer's rule. So x1 is determinant b1 over determinant A, x2 is determinant b2 over determinant A, x3 is determinant b3 over determinant A. So this is the solution vector x. Okay, and there's a short proof of Cramer's rule in the textbook, which tells you how to get this formula. And you can use similar way to get x2 and x3. To get so here we show how to get x3. So this is matrix A, and like this matrix A times this matrix. This matrix is obtained by replacing the third column of I by X. So this used to be 0, 0, 1. Now we replace 0, 0, 1 by x1, x2, x3. And we can see this multiplication. The result of this multiplication is this matrix. Okay, and this matrix is B3, right? So let's see the first row times the first column, second row times first column, third row times first column, we get A11, A21, A31, and the first row every row times this second column, we get A12, A22, A32, and each row times the x1, x2, x3, we get b1, b2, b3. Okay, so this matrix is B3, and then we take the determinants both sides, and we get determinant of A times determinant of this matrix. So this matrix is upper triangular matrix, so its determinant is equals to the multiplication of diagonal entries. So it is 1 times 1 times x3, so it is x3. It is, this equals to determinant b3. Okay, and since the determinant a not equal to 0, so we can move this term to the right hand side. So which means divided by both sides by determinant a, then we get x3 equals determinant b3 over determinant a. Okay, so there's a general form of this proof. If we let A to be n by n matrix and let A times this matrix, so this matrix is obtained by replacing S column of I by X. Okay, so you see this is S column. Okay, it is used to X 0 0 0 1 0 0 0 0. But now it is x1, x2, xn. Okay, it is x, and this result is equal to bi. And then we take determinant both sides. Then we get xi equals determinant bi over determinant a. Okay, and next is about the formula for A inverse. So A inverse is equal to C transpose over determinant A, where C is a cofactor matrix and ij's entry of C is a cofactor Cij of A. Okay, there is also a short proof in your textbook. You can see how to prove that. Okay, and here, so let's do some exercise. So problem 2 in page 2A3, use Cramer's rule to solve for y. Okay, you can see there's two variables here is x and y. We only need to solve for y, and this linear system is equivalent to this matrix A times the vector xy equals to vector 1 0. Okay, so now we only need to solve for y, which means we only need to find b2 because y is the second entry of this vector. So we only need to find b2. So b2 is obtained by replace second column of A by B. So we replace BD by 1 0. We get this B2. B2 is A1C0. Okay, and y is determinant B2 over determinant A, and it is equals to determinant B2 is A times 0 minus 1 times C, so it's minus C, over determinant A is A times D minus B times C. Okay, so this is y, and for the part B, we can this linear system equivalent to this matrix A times vector and equals to B. Okay, and we also need to know only need to know y here. So y is second entry of this solution vector. So we also only need to know the B2. Okay, so B2 is obtained by replacing the second column of A by B. Okay, B is 1 0 0. So we replace BEH by 1 0 0. We get B2. Okay, and y equals determinant B2 over determinant A, and determinant B2 you can compute determinant B2 by expanding the determinant by the first row. Okay, so it's A times cofactor C11 plus 1 times cofactor C12 plus C times cofactor C13. Okay, so then we get, okay, and here we use D to represent the determinant A. We get FG minus ID over D. Okay. Okay, now let's see the problem 6. Find A inverse from the cofactor formula C transpose over determinant A equals A inverse. Okay, so here we need to find a cofactor matrix. The cofactor matrix here is, so the first entry of cofactor matrix is C11. It is minus 1 to the power 2. This 2 is actually is 1 plus 1 times determinant. Remove the first row and the first column, we get 3071. So it is minus 1 to the power 2 times determinant 3071, so it is 3. And C12 is minus 1 to the power 1 plus 2 times determinant. Removes first row and second column, we got 0001, so it is 0. And by the same way, we get C13 equals 0, C21 equals minus 2, C22 equals 1, and C23 equals minus 7, and C31 equals 0, C32 equals 0, and C33 equals 3. Okay. So C is 300. Okay, the first row is 300, and second row is minus 2, 1, minus 7. Okay, and the third row is 003. And so you need to be really careful that we don't need the C, we need the C transpose. Okay, so the C transpose is 300 minus 2, 1 minus 7, 003. Okay, and the determinant A, you can use this formula, A11 times its cofactor plus A12 times its cofactor plus A13 times its this is times its cofactor C13 equals 3. So A inverse is 1 over 3 times this matrix C transpose. Okay, 1 over 3 times C transpose, so it is 100 minus 2 over 3, 1 over 3 minus 7 over 3, 001. Okay. Next, let's see part B. So this matrix A is a symmetric matrix. Okay, you can see it is symmetric about the diagonal, and since A is symmetric, A inverse is symmetric. Okay, here is a short proof of this result. So you can see if A is symmetric, which means A equals A transpose, then you take the inverse both sides, you get A inverse equals A transpose inverse, and A transpose inverse equals A inverse transpose. Okay, you can change the order of this transpose and the inverse. Okay, and so we get A inverse equals to A inverse transpose. So A inverse is symmetric. Okay, and by this formula, so we also know that if A inverse is symmetric, so the C transpose is also symmetric, which also means that C is symmetric. So we get this C is symmetric. So to find the cofactor matrix, we only need to find the entries in the upper triangular positions. Okay, so C11 is minus 1 to the power 1 plus 1. Remove first row, remove the first column. We got 2 minus 1 minus 1 2. so it is 3. And C12 is minus 1 to the power 1 plus 2, determinant minus 1 minus 1, 0, 2. Okay, remove first row and second column, it's minus 1 minus 1, 0, 2, so it's 2. So by the same way, you will get C13 equals 1, and C21 equals to C12 because the cofactor matrix is symmetric. So C12 is 2, then C21 is 2. Okay, and C22 is minus 1 to the power 2 plus 2 times determinant 2, 0, 0, 2 equals 4, and C23 equals 2, and C31 equals C13 equals 1. Okay, C13 is 1, so C31 equals 1. And C23 equals, okay, so equals 2, so C32 equals 2. And the C33 is minus 1 to the power 3 plus 3 times determinant, remove the third row and third column, so it is 2 minus 1 minus 1, 2, so it is 3. Okay, so this is C, and we know that C is symmetric, then it is equal to C transpose. Okay, and we also need to know the determinant of A. So determinant A is A11 times its cofactor plus A12 times cofactor plus A13 times its cofactor. So it's A11 is 1. A11 is 2. 2 times 3 plus minus 1 times 2 plus 0 times 1. So it is 6 minus 2 plus 0 is 4. Okay, so A inverse is equal to 1 over 4 times 3 to 1, 2, 4, 2, 1, 2, 3. Okay, here because C is symmetric, so C transpose equals C, so we just put the C here. Okay, so 1 over 4 times this matrix is A inverse. Okay, the last problem for this Cramer's rule, for this the last problem for this section is problem 10. It's in your in the page 284 from the it is to show that the determinant C equals determinant A to the power n minus 1. Okay, so we already have this equation, so we transform this equation to this one. Okay, so we times A inverse from the left side to both sides, then we get A times A inverse equals A times C transpose over determinant A, and then we times determinant A both sides, we get determinant A times I equals A times C transpose. Okay, then we take the determinant both sides, we get determinant A times I equals determinant A times determinant C transpose. Okay, be careful that when you want to take out this determinant A out of this determinant, you have to change the power of this determinant A to power n, to n. Okay, so this is determinant A to the power n times determinant I equals determinant A times, because we have this, the determinant C transpose equal determinant C, so this equals determinant C. Okay, then we divided both sides by determinant A, we get determinant C equals determinant A to the power n minus 1. Okay, and this equals to 1. Okay, that's it.